We have seen how to characterize random processes through the joint distributions of their time samples. Next, we will talk about the statistics or moments. And of course, the first thing we will see is the mean or the expected value of a random process. And in fact, the definition is exactly the same, except for the fact that now you have time dependence. Okay? Because the random process x of t is in general is a random function of time. When you take its expected value across time instants, the mean can be different. The definition is the same, but you use the PDF at every time instant. Okay, so when I ask you the mean of a random process, you will have to make it dependent on time. Okay, the time is significant in general. Okay, so sometimes for special cases we will see that the distribution may be the same across time, in which case the mean can be constant across time, but in general the mean of a random process depends on time. Okay, be careful about this. When we say constant, well, you have to be aware of what it refers to. Constant with respect to randomness, or constant with respect to time. Okay, the mean value with respect to randomness, it's constant, but with respect to time, it may not be constant. And the variance, again, the definition is exactly the same. So you have the second moment here, minus square of the first moment, which may or may not be time dependent. Now, we have used the concepts we have already seen here, but here we have two new concepts, autocorrelation and autocovariance. Auto here refers to the fact that this is a function that is correlation with the random process itself. So auto refers to that itself part. Um, this is the notation we use for autocorrelation, R sub x, T1, T2, and we have two time instants. And autocorrelation, in fact, is defined as the correlation between two observations of the random process at times T1 and T2. Okay? Expected value of x of T1 times x of T2. Now you have to be careful. The autocorrelation function defined in this way, in general, will not be equal to this, the product of the means. If you remember, I have warned you about this for two random variables. Their correlation, in general, is not equal to the product of their means. And this is the same observation here. Since the observation at times T1 and T2 are two random variables, of course, their correlation in general does not equal the product of their means. Okay, so in general, the autocorrelation function is not equal to the product of the means. In some special cases, it might, but not in general. And the other function we are seeing for the first time is autocovariance. This is the notation we use. And the definition is the same. It's the covariance between the random variables obtained by observing the random process x of t at times t1 and t2. So this is x of t1 minus the mean at t1 times x of t2 minus the mean at t2. Okay, so if you expand this, we will also see that this is autocorrelation minus the product of the means. Similarly for the relationship between the covariance and the correlation of two random variables. Now, as I say, I'm going to emphasize this once again. Be careful not to confuse time dependence with randomness. Okay, for instance, inside expectations, if you have some random function multiplied by some time function, this time function can come out of the expectation. It's not constant with respect to time, but it's not random, it's deterministic. Okay, so it's constant in the eyes of the expectation. Okay, it's not random. Its behavior does not depend on a distribution. So I can take this out, time function times expectation of this random function. Okay, be careful about this. Something that is not constant with respect to time may be fixed with respect to randomness. Okay, so here you have to be careful, for instance, by not confusing uh, time dependence and randomness. So here's an example. Let the random process x of t be defined as a times cosine 2 pi t, where the magnitude a is a random variable. We would like to compute the statistics of this random process. First, we look at the mean. It's expected value of a times cosine 2 pi t. And as I said, cosine 2 pi t, it's not a fixed number. It's a function of time, but it is not random. So you can take it out of the expectation. So what you get is expected value of a times cosine 2 pi t. As you see, this is the mean of a random process, and it's constant with respect to randomness. There is no random process, there is no random variable in this expression, but it depends on time. It's not a constant fixed number. Okay, be careful about this. What about the variance? The variance is defined in this way. This is the mean, this is the random process. And if you actually gather the cosine terms together, you get this. And the cosine term, again, it's not random, so it can go out of the expectation. And what remains is the variance. So you have variance of a times cosine square 2 pi t. Okay? And the autocorrelation here, by definition, is the expectation of a times cosine 2 pi t1 times a times cosine 2 pi t2. Again, the cosine terms comes out of the expectation. So what you have is the second moment of a times the cosine terms. And finally, let's look at the autocovariance function. It's autocorrelation minus the product of the means. So it's the second moment times these cosine terms minus this is the mean of x of t1, and this is the mean of x of t2. When you arrange them, you have these cosine terms again here. So you gather them together. What you have is the second moment minus square of the mean, which gives you the variance. So the autocovariance equals the variance times cosine 2 pi t1 cosine t pi t2 for a random process defined in this way.